Now, normally, I would turn over the microphone at this juncture to our program chair. However, on the occasion when the program chair does the talk, they have the right to delegate the introduction, and Dale has thankfully delegated it to me. So, I would like to tell you a bit about my esteemed colleague Dale Partin, who at this point should be familiar to all of you who've come to more than one meeting. Dale has served many boards in many capacities as a diligent secretary, treasurer, program chair, and all-around fabulous collaborator. And Dale is the rare person who thoroughly integrates a sense of wonder and faith with real hardcore science, and is a person who embodies the way in which we as a community of amateur astronomers can build bridges, connect, and educate as many people as possible. And it's an honor to serve with him. Dale?
And with you. Thank you very much. We have a special speaker for our main presentation tonight, and he's going to be talking about the chemical elements, their discovery, their properties. So the reason I decided to give this short presentation was to build a kind of a bridge between astronomy and chemistry. So this is a prep for the main presentation, okay? So, and I don't have much time, and it's a huge subject, so I love taking questions from the audience, but I cannot do that for lack of time. We can talk at the break if you have a question. So I'd like to ask you to begin by looking at your hand. Think about the chemical elements in your hand. You've got water in your blood and in your cells. The chemical elements that water's made up of are hydrogen and oxygen. How do those things first get synthesized in our universe? There's carbon all over the place in your hand. Your DNA has carbon in it. Your bones are largely calcium carbonate, so they have calcium in them. How did calcium get made in this universe? I chose this picture that you're looking at. It's one of the earliest pictures ever taken with X-rays by the guy who discovered them, Wilhelm Röntgen. Picture of his wife's hand. So obviously you can see bones which have calcium, but she's also wearing what I'm sure is a wedding ring. Probably has gold in it. So how did gold get formed in this universe? How did it all happen? Come on, slides aren't wanting to advance. Let me try this. That's not doing it. I'm not too happy about this. It was working a minute ago. Here comes
Tax report, it's the ID guy.
Weird. I don't know.
Did something.
At least that one.
Yeah, the touchpad is off.
Right?
Strange.
Use the arrow keys.
Yeah, well, shoot.
Boy, I didn't know that worked. I could just use my finger to advance a slide. Learn something every day. Okay, so here's a table of the periodic table of the elements. I don't want to go into it too much because our main speaker is going to do that. But just to say, these are the elements that have been synthesized in our universe. There's a huge amount of information here. For example, over here are metals, over here are nonmetals. If you take one column of the periodic table, say from fluorine, chlorine, bromine, iodine, acetylene, They all have very similar chemical properties. So there's a lot there. This is a good way of organizing things. But the question is, how did these elements get formed? Which way did I go? The wrong way. So, I mean, I don't have the time to go deep on any of this, but when the Big Bang happened, almost 14 billion years ago, it was extremely hot, too hot for any chemical element to exist early on. And in a very short time, it cooled to the point where protons could exist without getting ripped apart by high energy collisions. And if you have protons and electrons, you have hydrogen. So that's how hydrogen formed. And as the universe continued to expand and cool rapidly, it was just time for hydrogen nuclei, protons, to come together and fuse together to make helium. That was pretty much it. By the time helium was being formed, the universe cooled to the point where particles were not moving fast enough to hit each other and fuse. It's just a tiny trace of lithium, very, very tiny, the third chemical element that came out of the Big Bang. So, okay, how about the rest of the chemical elements? The question was, I think Bob asked, was it you, Bob?
Yeah.
Something about the first generation of stars. You get all this hydrogen and helium all over the universe, and gravity gradually pulls it together wherever it's a little more concentrated. It starts to come together from gravity. There's a big cloud of the stuff. And as it collapses in, gravitational energy is released, and that energy goes into heat. And eventually, it gets hot enough in the middle for hydrogen to begin fusing into helium, and so you've got a star. So the first stars were, this is not a talk about dark matter and dark energy. This is about chemical elements only. So I would say the first stars had only two chemical elements, mostly hydrogen, roughly 3/4 hydrogen, and roughly 1/4 helium. That's it.
Yeah.
If there were planets, that's all they had in them. I don't think there were, but I'm not sure.
Okay.
And so you get various size or masses of stars forming. I'd like to concentrate on what are sometimes called massive stars, roughly 10 times the mass of our sun, because they're much more efficient at generating heavy chemical elements. So for stars with a core temperature on the order of 10 million degrees, like our sun, hydrogen can fuse, and ultimately, I don't want to give the details, but there's a process by which they fuse to generate helium. That's what's going on in the sun right now. That's where the energy comes, percolates up to the surface, makes it hot on the surface, and the sun shines, right? That's where sunlight comes from. Fusing hydrogen into helium. That works fine at this kind of temperature. These particles are moving fast enough at that kind of temperature that they can overcome their electrostatic repulsion, because they're both positively charged protons, and collide and fuse. And they can spit out a positively charged electron and form deuterium, which can then fuse to form helium. However, at this temperature, you cannot fuse helium. You've got twice the charge, positive charge here and here, repelling each other. And these things are heavy, so they don't move as fast. So when they are on a collision course, electrostatic repulsion pushes them away from each other before they get close enough to fuse. You need higher temperatures, like 100 million Kelvin and up, to fuse helium. And then you can get beryllium, and then you bring in more helium, and you get carbon and more helium, and you get oxygen, and on it goes. Well, how far does it go? Is that the process which generates the whole periodic table of the elements? Answer is no. I'm sorry, I'm going to have a couple of graphs in this talk. If you're not a graph person, don't worry about it. Just go with the flow, get the big idea, that'll do, okay? This is a graph. On the horizontal axis is atomic mass number. That's roughly speaking the mass of the protons and neutrons in the nucleus. This way it's binding energy per nucleon. A nucleon means either the sum of protons and neutrons in a nucleus. They're both called nucleons. So you take the number of nucleons and divide it into the binding energy of a nucleus, and that's what's being graphed on this axis. So here's heavy hydrogen. When it fuses, it gives up a whole bunch of energy. Comes up to form helium. Again, that's where our sun is getting its energy, burning or fusing hydrogen to make helium. And you can keep fusing things if the temperature is high enough, which again is not in the sun to efficiently do this process. So you can make carbon and oxygen and other elements up until around iron. At that point, if you try to add another, fuse another helium nucleus on here, you need, instead of getting energy out by reducing energy, you have to start increasing the energy of the nucleus. So it doesn't want to go that way. So, for example, the picture I showed with the gold wedding ring in the X-ray picture, you can't make gold that way, or other heavy elements like uranium. Rather, if anything is going to happen, it's going to be not fusing atoms together going this way, but fissioning atoms to go this way toward iron. So iron and elements near it like cobalt and nickel. Iron has the most stable atomic nucleus. It's the most strongly bound together. This is why the Earth's core is mostly iron, because a lot of nuclear processes in stars stop when they get to iron. The story is sort of more complex than that. That's sort of the big picture. In high-mass stars, as fusion happens, and again, the core is really hot in these big boys, you get shells or layers of elements with iron in the center, at least concentrated in the center, and working out to lighter and lighter elements till you got hydrogen out here. So that's what happens, and so you gradually get to the point where no heat is being produced in the center, or not much, depending on how pure the iron is there. And so, without generating heat there to push back against gravity, to generate pressure to push back against gravity, the star gets to the point where it's going to collapse. And when it collapses, it gets really hot then, because, like 1 billion Kelvin or something in the center. And then it explodes. That's a supernova. And so all these heavier chemical elements, up to about iron, gets thrown out into interstellar space. And they mix with more hydrogen and helium left from the Big Bang. So that's fine. That stuff mixed with hydrogen and helium forms the next generation of stars. And planets, because now you have a small amount of heavier elements up to iron. The down arrow key works now. I don't know why. But what that gets us is, I put these two circles on here to roughly show you the elements that can be formed that way. That's only about 1/3 of the table, the periodic table of the elements. that's, there's an important part of the story that's missing. Let's see. So, this is the second and last graph, okay? So again, don't let me lose you. On the horizontal axis is proton number of protons in the nucleus. This axis is number of neutrons in the nucleus. So, and this red line here shows you what you would get if the number of protons equal the number of neutrons in the nucleus. That works. They're about equal up to about iron. And then, if you go up this way, the material is increasingly radioactive the farther you get from this region of stability. You go either direction, I mean, right down the center of that, you get stable atoms or nuclei. If you go to the edge and beyond, in either direction, it's radioactive, and the tendency is the farther you go, the shorter the half-life of the isotope is. It can get way below a billionth of a second, way below the farther off you go. So, by the time you're up to gold, atomic number 79, you need 1.5 times as many neutrons as protons to keep it stable. Crudely speaking, what the neutrons are doing is diluting the protons. So the electrostatic repulsion between them is not so great as to make the nucleus unstable and it comes apart on you. So that's a hint. There's a hint in this chart, this graph, about what you have to do to get stable nuclei beyond iron. You need a neutron-rich environment, right? That's what you need. You can't just take 2 iron nuclei and slam them together. That would put you up about here, right? And that's not stable. So you need something with a neutron-rich environment. How do you get that? Where do you find that? Now let's see if I can make this work. This is a 2.5-minute video.
It's not playing on the screen.
Oh, it's not?
Nope.
Ah. Let me see if I can.
IT man.
That's whatever I can. I might need your help to get back to where I was after this. Let's just do this.
We've got 7 minutes.
Nice music. Something happened. There you go. You're in.
I'm gonna go back.
Okay, with a little magic from our IT guy, I'm back online here. So now when these neutron stars collide and then explode, you not only have elements up to iron thrown out into space, you got the entire periodic table of the elements. I've read that analysis of the elemental composition of the solar system suggests that there were at least 2 different types of supernovae that seeded our solar system with elements. And after that happened, our solar system would have looked like this at one stage, where gravity pulled a big mixture of that material, including more hydrogen and helium, into a rotating disk. A star ignites in the center. This is looking actually at dust, the temperature of dust in another star system. And you can see these dark rings where planets are forming and collecting all the dust from their orbit, with a whole bunch of planets forming. You can try to count the dark spaces yourself. So I realized this was quick and not super deep, but it's just a quickie. This is the big picture, the picture from 10,000 feet, so to speak, of the story of where the chemical elements came from. Okay? Thank you for your attention.
All right, thank you, Dale. So it's now time for a snack break. We've got a selection of snacks up at the front that were provided by Dr. Jerry Dennefer, so let's give Jerry a round of applause.